Hey everybody, it's Mr. Zabo coming at you here with our third installment of triangle centers and points of concurrency. Today we are going to talk about the incenter. So far we have talked about the circumcenter, which comes with our perpendicular bisectors, and we talked about the centroid, which comes with our medians. Today we're going to deal with the incenter, which is the point of concurrency of the three angle bisectors of a triangle. And again, there are a couple of key facts about our incenter. It's equidistant not to the vertex, but to each side of the triangle. And so you have to remember that when we're talking about distance to the side of a triangle, it's always the perpendicular distance. It is not necessarily going to a midpoint. It is going to that side, but it is going to be this incenter to the side. That segment will be perpendicular to the side. Therefore, it represents the center of the circle that is inscribed in the triangle. And we will get a chance to take a look at what that means. As you can see in our acute right and obtuse triangles, there's a lot of things that are happening. First of all, the incenter is inside these triangles. It's in the interior section. Second of all, you have bisected all three vertices with your angle bisectors. That's going to give you a lot of information about your angle measures. Third, I had to draw in a new segment in most cases to get the perpendicular distance, and that's what I've done here in pink. So segment GE is not the perpendicular distance. That's just the rest of the angle bisector of the vertex C. So that does not necessarily meet here at a midpoint. It doesn't necessarily meet here perpendicular. So you might have to assess a new perpendicular segment. These three pink segments are the congruent segments, not EG, DG, and FG in any of these. Third is that you do now have these perpendiculars. So you do have other triangles that you have built in here that have an angle that has been bisected, so the half of that vertex, a right angle, and then you can figure out a third angle measure to get another triangle. Lots of different things that you can do in incenter type problems. You've got to be careful though that you don't look at segment BG and segment GC and consider them congruent. That's when you have a circumscribed or perpendicular bisectors. This is the inscribed circle. All right, now let's take a look at sketching a few options. Take a minute here and see if you can take these triangles and assume or estimate where that incenter would be by trying to sketch the angle bisectors. Pink here is the point that should represent the incenter. You notice we've bisected the three angles with my blue segments. The pink segments I had to draw in the radii, those are the distance, those are the congruent segments. So I could go through and mark these three as congruent. Those are the only three congruent segments that I know for sure. It would look something along these lines, and again, these have been bisected. Now, if you had watched my angle bisector construction video that was on the other side of that screen, then you would know how we can actually use a compass to bisect these. Other options are to fold a piece of paper exactly in half, so ray GI is folded on top of ray GH. The crease should go and be that blue line. It's another way to do it without a compass. All right, now, what's important about these? So first of all, we have to be able to look at diagrams and just look at these marks and figure out exactly which point is being referenced here. So what is this point? Well, we've learned 3 points so far, and they come from our 3 different types of segments from triangles. So you have to be able to match those up. Take a minute, press pause, and write down what is the name of the point and what are the segments that formed them here. On problems like these, it's key to first identify what are the segments that we use to form these. So these are our perpendicular bisectors, these are medians, and these are angle bisectors. Now we should be able to draw that connection. Perpendicular bisectors, those formed our circumcenter. And our medians were the first one, that was the centroid. And the angle bisectors was the one from today, our incenter. And those now tell us the properties that we can apply and use both algebraically and with coordinates as well. All right, so that's if we don't tell you the center, but just have our segments marked with the tick marks like that. Now, here's our first practice problem. We are telling you in here that it is the incenter. Lots of information that you can glean off of that. See if you can identify the length of AB, the measure of angle JAD, and the length of segment AG. So this 12-degree angle is down here, angle AGD. 41 degrees is angle AHC. Segment CJ is 21, and segment AJ is 29. Part of this was by finding angle measures. Lots of different ways to do this, using many different types of angle measures. I took the entire triangle GHJ, and if this is 12, I knew that angle HGJ is 24. I knew that angle GHJ is 82, which means angle HJG must be 180 minus the sum of those two angles, so it's 74 degrees. I'm bisecting that 74 degrees. This angle AJD is 37 degrees, and then its complement is going to be the angle we're looking for, angle JAD, or 53 degrees. So that since it's an incenter, AD, AC, and AB, those are the perpendicular distances to the sides, must all be congruent. Then I have a right triangle where I know a leg is 21, a hypotenuse is 29. Well, if I had a 20 as my other leg, that's Pythagorean triple, or I could use the Pythagorean theorem if I didn't recognize the triple, and find that segment CA must be 20, so AB must also be 20. Now the last one is segment AG, but this one's a little bit trickier if you don't think a little bit about some of the other stuff that we've learned this school year. So if I'm looking for that segment and all I know is, well, that's 20, this is a 12-degree angle on each side, how am I going to figure that out? Well, if you don't see it already, let me draw this triangle out and see if we can recognize what to do. And we're looking for this. Well, we did this earlier this semester, and this was our trig unit. In order to find and estimate what this is for side AG, or x here, I'm going to have to use my sine function because it's a right triangle, and I can use a trig function here. The sine of my angle measure, 12 degrees, is equal to the opposite side length divided by the hypotenuse, which in this case is segment AG. So when solving this, segment AG is going to be equal to 20 divided by the sine of 20 degrees. Don't forget, you always have to check that your calculator is in degree mode in this case. Get that AG is about a length of 96.19469 and so on and so forth. All right, so on all the other centers so far, we've gone straight from here to coordinates. And good news is, it is possible to find the equations of angle bisectors and the coordinate of an incenter, but we're not going to ask you about this. This is a little bit beyond where we need to be right this second based on the current situation of remote learning, but it's something that you definitely can do if you're interested in looking it up. There's a lot more complexity to it with angle bisectors, but it's not something that's impossible. So we are only going to hold you accountable to understanding how it comes about, basically from the angle bisectors, and what it means, that you have angles that have been cut in half, that you have perpendicular segments that are congruent, that the incenter has an inscribed circle. So those are the things we will hold you accountable for. All right, and there's going to be one more installment of points of concurrency with triangles, so go ahead and get yourself all prepared with the first three, and tomorrow we will introduce our fourth and final triangle center.